Actually set up here with the stuff so I can step the drive and turn the drive select on and whatever, and I can scope. That's the index pulse there, by the way. The LEDs on this thing, of course, are active high, and the logic of the drive is all active low as per the ST-506 standard, so you have to just remember that each LED is on when it should be off if you want to think of like a certain line being active, the LED's out. Same goes for like my drive select switch. When that's low, that means the drive is selected because it's active low. So I've got momentary switches up here. They can just spring back. This one is going to step the heads. This switch toggles to select the direction in which the heads step. So that would be to step away from the index track, or not the index track, I should say the track 0 or the landing track. That steps away from the track 0. And I've got little bits of tape here and written on, so the ready indicator, which being extinguished means the drive is telling me it's actually ready. The index, there's no use in having that LED even hooked up. The pulse width of the index pulse is so short that deselecting the drive or selecting the drive makes no visible difference, but you can see it on the scope. And track 0, of course, is extinguished, so we are on track 0. If I deselect the drive, they all should light up as they do. And of course on the scope, my index pulse is gone. Select the drive, there's the index pulse again. So you can see deselected, selected. And of course, if I move the heads off of the index, I keep saying index, that's nothing. Index means that the drive is at the beginning of the first sector of a given cylinder, which is, a cylinder is a way of saying a given track on all platters. So yeah, index is just a pulse, a timing pulse that recurs for every rotation of the motor in the drive. And this pulse is actually coming from the motor drive assembly. It has nothing to do with anything written on the platters. And of course, I'll demonstrate in a minute that there's a fair bit of jitter between the index pulse and the data that's written on the platters. And we're talking raw data here. This is everything, including the formatting data and the whole bit, not just the data the computer itself would store within a given formatting. So it's, being an RLL drive, it is going to be or RLL or MFM. The clock is encoded within the data, just like we have on CDs and a few other types of things like SPDIF or Toslink. Most of these things use a sort of variant of Manchester encoding. It can be Manchester, it can be differential Manchester, and there's a few other different things like biphase mark encoding, which are all variations on the theme. The point of this is that there's no separate tracks for clock. The clock and the data are recorded on the disk at the same time, and they must be decoded. And this is why RLL is harder to decode than MFM, is because we're increasing the data density by recording the clock information less often, which is nice to save space, but it does mean the system has to be more precise in terms of its phase noise, or it will interpret the data in the clock incorrectly. And there's no way to recover from that at all. There's nothing you can do. You need to know that the clock and data are being decoded correctly, and so that the data values arrive within the correct slots. Otherwise, the bits themselves essentially are interpreted as being bits that belong to other points in time, or if you're thinking of it in terms of data words, say a byte, an 8-bit word, your data bits can end up in the wrong parts of the byte, rendering the byte absolutely useless. It's one good reason we have error correction, parity, cyclic redundancy checks, and so forth. So anyway, yeah, that's kind of what the index pulse is, just there to tell the controller when a track begins. But it's up to the controller to incorrectly record the track data into its buffer and interpret the data and will separate the clock and data correctly and record the data correctly. And that's all going on in a specialized piece of electronics known as the drive controller. in the computer. And you'll see, again, like I said, the amount of time between an index pulse and the actual data pulses, the beginning of the data pulses of a given track, wobbles around all over the place. It looks to the human eye, you know, if you have it, you know, zoomed out, where I have here, you can see the beginning of a track here and another one begins there. So this is a rotation of the platters. If I were looking at it on this scale, if I had my data hooked up to this trace, you wouldn't see a relative variation visibly there. But if I zoom in enough that you start to see individual data bits, which is quite a shorter time scale, there's a lot of bits in a track, you're going to see that there's quite a bit of wandering around. So you can't even get this thing triggered on the scope where you'll see steady data. It's good enough you can see it with your eye, but it's jumping all over the place. So the only way to scope this would actually be to use something like a digital scope that's going to record a single trace of, once it's been triggered basically, into memory, and then you can continuously display that. On a live view scope like this, it's drawing another iteration of the same data on the display every time it sweeps. And if it doesn't draw them in the same place every time, they become very difficult to visualize. And I can't tell it to just take one sweep because, well, then I'm not going to see that go by. Geez, that's just goes blip and it's gone. And good luck doing that on a storage scope, a conventional one, because there's no way you're going to get the screen to write that fast. So we need digital storage oscilloscopes to do this, or better yet, logic analyzers. A logic analyzer is the correct tool for this job, or at the very least, some type of data acquisition system that will accept a trigger, and as soon as it's being triggered, record whatever the hell it gets. And that can be done synchronously or asynchronously. If it's done in an asynchronous manner, which is how this is all intended to be done, it has to have enough bandwidth to allow for the fact that there's, you know, it may not be decoding the clock out of the information coming off the drive. So it's just going to work in a more smooth analog sort of way and record whatever it gets whenever it gets it, just like a scope does. We don't care about amplitude variation at all. This is the output of the drive is logic level. It's just being amplified and clamped and spat out by a gate. So we don't give a crap about that, but we do give a crap about linear and smooth variations over time. Whereas if we use a device that is actually interpreting separating the data and clock, ergo a data separator, then we don't care about, you know, temporal resolution really at all, because we have defined the slots in time into which the bits should go, and the system's decoding them for us and just showing us the raw output, which is really the job of the disk controller. So I'm kind of going on at length about this. There's a lot to this to understand, to see that there's a lot of subtlety and nuance to exactly what's going on. So yeah, going back to this, drive is selected because the ready light is out. Track 0 is out, which means I'm on track 0. I'll step the heads one step outward, and blink, there comes on the light. And I can go back again, and the light should go out. Right? And if I can count, say I'll go out 5 steps. 1, 2, 3, 4, 5. If I remember and I count back the same amount, it should go out. 1, 2, 3, 4, 5. That's how the controller works. Until the drive is low-level formatted by the controller that it's going to be married to, the controller has no idea what track it's on or what sector it's reading there. Well, sectors don't even exist at this point. Tracks exist, or we'll call them cylinders, is what we're using in the CHS numbering system. The only way it knows what cylinder it's on before it has a low-level format it understands is by keeping track. It's fully open loop. It has no clue. And you can get drives where you're trying to low-level format them, and the head actuator gets stuck, or it's a little sticky, and some of the time it sticks, and other times it doesn't. That's a problem, because you need it to work absolutely reliably, at least long enough to fully low-level format the drive. Once that's been done, any controller I've ever heard of records the sector number, the cylinder number, I believe also the head number, so the full physical address of the location of the data on the drive, right down to the sector. That's all recorded at repeated intervals on the disks. It's part of the low-level format. So the controller doesn't need any hardware-level feedback except for the index pulse to know when tracks recur. Other than that, if it successfully records and separates the clock and data, it'll always know where it is if there's a good low-level format, which is nice because, you know, if the motors are a little sticky in the head actuator or something like that, it'll know, oh, I stepped the heads, but I'm not getting the correct cylinder. I'll try again. So there's a little bit of redundancy there. You really do need closed-loop control as much as possible. And this is why on modern hard drives we did away with the whole stepper motor thing and went for full closed-loop servo, and there's physically a servo track written either on its own platter, on its own surface, or at least on modern drives, it's written on every surface of every platter next to the data or in with the data, something to that effect. So the drive has a lot more detailed feedback about its location. Reason being that as areal density increases, the tracks become so finely spaced that you can't use a fixed distance mechanical system like a stepper motor to select them, because the thermal expansion of the platters is greater than the distance between tracks. Like, it could be a good number of tracks wider. The platters will actually, you know, expand that much. You would never be able to find a track. So instead, we just forget about all that. We actively compensate by reading where we are all the time, no matter where we are. The very latest stepper motor positioned discs actually did this, and they used micro-stepping. And so they were using conventional hardware, but the algorithm and the topology of track selection was actually more modernized. Seagate ST-238R comes to mind. That was quite a drive. I think by the 4096 we were using, yeah, that's a voice coil actuated drive, so I'm wrong. There were some late drives that would micro-step and positioned based on servo track information. And actually, a bit of curiosity trivia here with old drives is, if you see drives with an odd number of heads, that's why that is like that. They would never waste a surface of a platter. I mean, they could, but the reason there's an odd number of heads is that the last head that you'd expect to be there is actually being used for a servo surface on one side of a platter. It's a spare surface that's all servo information. That is not low-level writable from the outside world. I mean, it might be on some drives under certain circumstances, probably under manufacturing circumstances that you'd have to know the procedure and the protocol for rewriting that. And it is why that, you know, as drives started to get more modern, if you demagnetize them or you get them exposed to a powerful magnetic field, they're junk. You cannot make the drive work again. It's not even that you can't get your data back. You couldn't even write data back on it if you wanted to, because the drive has become blind. It has no idea and no means to locate anything on it. It has no idea where it is. So it's junk, you know. That's one nice thing about drives this old, is that they are so dumb and so crude. I mean, from contemporary standards, you could absolutely wipe the platters, all of the platters on this. It uses all the platters for the data. There is no servo or nothing like that. In fact, I've taken these apart and mixed and matched platters, flipped the platters over, swapped them, cleaned them in the sink, you know, like literally, I mean it, I've actually done this, and put them back together. It doesn't matter whether the platters are in the same angular alignment, if they're in the same place. I mean, it does if you want to get your data back using the same controller. But even then, it still works. You can actually, as long as they're all platters out of the same drive, if you have data on a drive like this, and you pull out the platters and mix and match them or whatever, I mean, you can't flip them upside down. that does actually fuck everything up, because the controller is not expecting the encoding to be played to it in reverse, although there's no reason why you couldn't still read that if you made up your own controller. As long as they're all turning in the same direction and you mix them up, it would just be a matter of changing the head selection. So you could fool this whole thing to work with the original controller by rearranging the addressing of the heads, which would take a little bit of logic circuitry, because the the head addressing is encoded by a 4-bit word, or 3-bit on earlier drives that use reduced write current. So you can't just move wires around. You'd actually have to use a little bit of logic to reorganize, you know, what 3 or 4-bit encoded head address translates to now what head you think you're getting. And I haven't tried this yet, but I'm confident it would work. There's no reason why not. Relative angular displacement, I don't know how much that matters for most controllers, but I'm sure there are plenty for which it doesn't care. Some might bitch at you because the index pulse starts too early or late for the beginning of a track. So that could be a real issue. It probably does matter for most of them, honestly, because they're going to be expecting, you know, a certain limitation on the skew between the index pulses and when the track was, you know, started. But again, as long as you could compensate for that time delay, there's no reason why you wouldn't be able to use the drive this way. It's just kind of these are my thoughts. This is what I think about when I'm falling asleep at night, trying to think of how can we screw with this and make it still work. Well, it turns out there's a lot of ways. But anyway, going back to looking at the data actually coming off this thing, I'm going to try to plunk the phone down here so you can look at the scope while I'm actually scoping this. I should have attached a cable and everything to the drive so I could leave the scope connected while I use my hands to deal with everything else, but of course I didn't do that. So I'm just going to park the phone on top of something here so we can just, hopefully it'll stay put. Not overly great positioning, but well, here I'll lift it up on top of something a little taller. We're real professional, all right? I don't have any video equipment really. I should invest. Yeah, good enough. Hopefully it stays put. All right, so you can see the index pulses, and the scope is triggered to those, which if there's no phase noise, no jitter, that would be fine. I could zoom in on the time base and I would see stable data, and I wouldn't need to worry about hold off or anything like that, because the scope would only be sweeping once per revolution. The display would be dim, because that's a long period of time given the data rate. But you'll see what I'm saying here. Like if okay, now I'm on the data, and right now it looks like nothing. You can just see, you know, even if or am I on the data? Let's see. Yeah, that's definitely data. You can see it's kind of fuzzy. Maybe I wasn't on the data the first try. Anyway, let me find a better spot to stick the probe here. Apologies, I should have planned this. Okay, I'm in a blob of solder instead of Enig. It's a little less slippery. So I'll hold that there and move this up so you can see that it's distinctly separate from the index pulse. Oh, that looks terrible on the phone camera. Anyway, yeah, you can see the data is kind of fuzzed in there. Turn the intensity down a little bit. So, yeah, if I zoom in, you start to see turn up chopping. You see how many bits of data there are in between index pulses. I mean, there's data pulses. Okay, so the index pulses are now stretched out to the point where they're halfway across the room, and we still have, you know, 2 bits per div on the scope. Let's just give you an example of how much data there is in a track on a drive. And this is on an old drive. On a modern drive, I mean, this would be orders of magnitude more pulses per index pulse. Quite a bit more. So now we're zoomed in to a point where if there was no timing skew, I would have nice data. I could use the delayed triggers and I could scroll along and I could look at every single bit. In fact, I could read the data and interpret it by hand on the scope, every bit of the whole track if I wanted. But I just don't have enough stability between the index pulse and the actual data to read that by eye. I mean, if you were to sit and kind of stare at it for a while, you could probably figure it out, but it would suck. It would be nice if it was a little bit brighter. There's nothing I can do about that right now. Scope, the phone doesn't really like this at all. I could turn off channel 2 so we don't see it. Maybe that's a bit nicer. Kind of. So you can see, if you're watching, you know, it's not jittering so much that we can't see the same data, but it's too much to do much about. I'm not going to attempt it right now while I'm holding the scope probe on there, but I actually tried wiggling the drive, rotating, you know, like a rotating wiggle about the center of the platters, and sure enough, you could see the skew increase, and it had a correlation to the frequency that I was wiggling the drive at, which bears out the point. And it's just due to, probably mainly due to error in the way that the index pulses are retrieved, because they're just being read as a magnetic pulse off the motor drive. There will be a tab or a little bit of a hole drilled partway into the rotor, which goes past a magnetic reluctance sensor or a Hall sensor or something like that. Some of them are optical. Whatever they've done, you know, the Hall effect ones tend to be quite clean, but the magnetic ones can really have a lot of wobble going on. There's just too much variation from temperature and from stray fields and stuff. And it's just, we're talking, you know, I don't know what the data rate, I think the data rate on these drives is 5 megahertz. Or being RLL, it might even be 10 megahertz. So we're talking, you know, 500 nanoseconds is all it has to vary to move a whole bit over, right? That's 500 nanoseconds relative to the rotation of the platters. Tiny! There's no way it's going to be that stable. Anyhow, if I trigger on the data, see, now we got very stable data, but the problem is that the scope is going to re-trigger too often for a track. And so what we're going to see is the scope re-triggers and begins a new sweep every time it has both ended the previous sweep and seen another edge that matches the slope that it's looking for, which is unfortunate because it means it's going to display a whole bunch of different pieces of a track that appear overlapped, and that's what we're actually seeing here. This is the same reason why when you're looking at the EFM pattern on a CD player, you see what appears to be a fisheye pattern, and what it is the fact that persistence of vision and the persistence of the scope phosphors, of course, is adding up a whole bunch of different pieces of a wave, of different pieces of different waves that would look a lot different if they had all started on the same exact trigger point. I'm not really describing that very well, but I could actually do another video showing that. And I've even actually set up a way of arranging so that you can pick, you know, whether you want the wave to start once per revolution or once per data word or whatever. You know, per data word is really what you want. And by that I mean not packet, I forget what the word is. Oh, come on, someone put it in the comments, I can't remember. In a track on a CD or on a hard drive, whatever, say it was every sector. We can call it, CDs are divided into sectors. All I'm saying is that if you were to view the data repeating at the right point, ergo at the beginning of every sector, which is just the way we divide the packets, as it were. These would be packets if we were looking at them on a TCP/IP link, and they're doing the same thing. If we always triggered at the beginning of a given chunk of data, then it wouldn't look like this, where you've got what appears to be, you know, whatever is the same each time or more similar appears brighter, and whatever is a little more different each time it triggers is going to appear dimmer. That's really why it looks like that. So anyway, if I increase the hold off, and this is something everybody should know with scopes, hold off adds time delay at the end of a sweep in the time base. So once it's finished a sweep, hold off, if you add some more hold off in, it means the scope will wait a fixed amount of time before it will accept, it'll like enable the trigger to be re-triggered, or arm the trigger, as we say. The unfortunate thing is that the amount of hold off you need to see this is quite a bit longer than what's offered by this scope. Some scopes have hold off that you can vary out into like quite extreme lengths of time. I mean, in a storage scope, that's useful to have out even into the seconds or minutes if you want to make sure you don't re-trigger before an event has recurred. You don't want to be re-triggering partway through the event, which is really what we're seeing here. That's what the hold off is for. So yeah, you'll see that it gets dimmer, but what we would see if the hold off was long enough is you'd actually see this clear up, and like actually portions of this would just flip out of existence, and you'd start to see start to seeing it triggered more in the same place and displaying only that data. But even then, the hold off can't really save you, because the whole thing has no way to know whether it's at the same point each time. It's all about coincidence, really. So you're looking to set the sweep so that it's roughly the same length of time as the span of data, or whatever it is you want to look at, which is impossible if the span of data is so data dense that it wouldn't fit on the screen, which is exactly what we're dealing with here. We've got a period of whatever, this is turning at 3600 RPM. So what is that, 60 milliseconds or so? No, whatever. If I can't do the mental math right now, but the reciprocal of 3600 in seconds, in minutes, I should say, that's why I'm getting lost here, is the span of the entire clump of data. And we're trying to look at, how many microseconds of it? 500 nanoseconds of that data. Not good. The other way to do this, I'm just meandering, ignore me if it's not interesting. I think this is interesting, that's why I talk. You could, I wonder, put it in the comments if you know this. If there should be such a thing as a scope that instead of having a hold off, has a hold off input. In fact, I'm a bit surprised I've never seen that. I have never thought of this before until right now, literally just thinking of this. This is why I like to daydream. If you have a scope with a hold off input instead of just a hold off knob, you could use the index pulse to say, okay, arm the trigger now, and then when the beginning of the track occurs, instead of seeing the skew causing the track data to blather all over the place, you would always have this nice stable locked in thing, because it's not actually triggering on the index pulse. It's just preparing the trigger, saying, okay, get ready, and we don't know when this thing is coming, but it's very soon, and it allows for some variation. I'm going to have to look into that. I actually would love if that was a feature that a scope had, where you could just have a trigger input and an arm to the trigger input, and maybe some filters still, and I still need a hold off knob in case the variation is a little different or more or less than you want, and so you can always pick the same thing. That would be nice. I think that's basically what if you look on most scopes up to a certain age, older than a certain age, you'll see they've got in their trigger modes usually TV line and TV field. It's also SGL field. I forget what that was. These are special ones that have their hold off programmed either in an analog circuit, or in this case, the scope probably is all done in software, to match the known field and line rate of television. that's a case where you can get away with having presets, because television sync, line and field rates are very tightly defined. They don't tend to vary at all. They have to be very strictly controlled. And even if they weren't, having a mode like this, it'll generally lock in and show you just a line or just a field all on their own without having to get crazy with the triggers and hold-offs. Because again, a TV is actually another example of a serial data channel that has a low repetition rate for the data rate. Like a TV has, say it was just black and white TV, RS-170 composite video. I can't remember what the video bandwidth, I mean the whole thing has a bandwidth out to about, for monochrome I can't remember, for color it's like 6 megahertz or so. The point is, the frame rate is 30, the field rate is 60. Am I getting that right? The frame rate is 60, the field rate is 30, it's interlaced. The line rate is 15,750 approximately. That's the high frequency pitch you hear, horizontal scan. But the video bandwidth is in the megahertz. So it's the same problem you run into that you've got with the hard drive here, which is exactly why I use it as an example, because if you're trying to look at, 5 million bits or 1 million bits or whatever it is, transitions, pulses, something, cycles of wave, over a repetition rate of, once, say, 60 times a second or something, the ratio is enormous. The timings are just not going to be tightly controlled enough to keep the jitter from bothering you or making it impossible to analyze the signal at all. That's about all I can really say. One thing I can do is I'll step the heads on this drive, and you can watch the differences in the data, and you will see something interesting. I'll go back to track 0. That's track. Oh, I was on track 0. That's just it doing a reset sweep. Yeah, drive select off. There's nothing. Drive selected. I've pissed off my trigger. Let's see. Let's do this. Okay, go back there. All right. Sometimes this gets you away with a little bit of a fake hold off too, but that's not working. Anyway, yeah, if I step... Oh, see, there's a very different looking... The data, whenever it's retriggering, happen to be more coincident in this track. I don't know why, but that's it. It's a little easier to discern something. I'm going on to the next track. Ah, that's interesting. This is a bit more like what you see with the EFM pattern on the CD player, where you've got a whole series of different frequencies occurring repeatedly, and that's how they stack up when you re-trigger this often. You're going to have integer multiples of some low fundamental frequency. It could be as low as the frame rate, and then anything above that depending on basically the run length. That's what run length limit means, is how many, really it means how many cycles of nothing are you allowed between having a cycle of something, because the system needs to lock its clock back on sometime, or eventually it drifts too far to interpret the data. This is really what we mean by clock recovery. But yeah, if you see something like this where it looks like you see a little bit of periodicity in the brightness. You see there's a bit of a bright spot there, there. So that's showing me there's some coincidence going on between sweeps. So many successive tracks, we're getting a little more of likelihood of this stuff being occurring more often here. It's kind of like a Fourier analysis, honestly. And then the spots where the same pulses look dimmer, that means they're occurring less often. There's a lot of tricks on scopes you can do, where you're visually interpreting a lot of information that's not just taken for granted, but it's subtle. If you know what you're doing, you can glean a ton about something, even if you're not analyzing it in the discrete way. Even if it's just a statistical determination, which is what I'm making here, you can determine a ton from that. And you'll see this on pulse density encoded channels. You'll see it on, what are they? delta sigma modulation, stuff like that. You may not be able to see the full encoding going on because everything is changing too fast, but you'll see brightness differences because of how often over time things are repeating. That's useful anyway. So going on to the next track. So now we have a coincidence going on at a little higher rate. A couple of different rates there you can see in the intensity variations. Hope that's visible on the screen. Going back to a little more of a discrete. Okay, and then this is what I found after about 5 or 6 tracks. It's the same. Nothing's really happening, and I'm pulsing tracks here by hand, and that is what I would expect. This drive was low-level formatted, and I never wrote anything to it. So probably the first few tracks contain pertinent file table information because I did a low-level and a high-level format. So it stands to reason that there should be, a couple of tracks that have unique things going on. They're going to be identifiers, file table information, because this is going to be FAT16. So literally your file table, and then file allocation. That's what I was trying to come up with. You get a few tracks in, and then there's just going to be all we're seeing now is index portions, index frames. Basically, it's telling the controller, okay, here's sector number 2 under head number such and such on such and such cylinder, and it rotates it a little more. Here's the next sector of that same cylinder and head, and on until you finished all the sectors of that track, and then we start again, and then just blank space in between where there isn't anything but clock pulses as a requirement of run length limitation to keep the PLL in the disk controller in sync with the drive. So if I was to keep stepping along, I would expect to see this same stuff recurring endlessly until the end of the disk. If I'm remembering my stuff, I haven't been doing much computer stuff for a while here, but if I'm remembering how FAT works, there should be a track or two at the end of the disk that repeats some of the information that was seen at the beginning. That's there for redundancy. It's to help make it possible to recover a drive that's lost its file allocation table. I don't remember what version of FAT they introduced that with, but it wasn't always there. And it's still a shitty system. I mean, Digital Equipment Corporation, figured their shit out a long time ago and came up with their file table systems for VMS, all of which NTFS is based on. In fact, Windows NT is heavily based on DEC VMS because the engineers from DEC were directly involved in creating Windows NT. Anyway, kind of off on a tangent here, but DEC, Linux, and Unix systems or whatever, they were really moving to journaled file systems and different types of things that have things like inodes or whatever, stuff at repeating intervals all over the place that could be used to help reconstruct a file table. FAT was terrible. It's still terrible. I don't like it, but that's kind of why this is the way it is, and I'm just kind of going off on my tangents. I'm almost 40 minutes into gabbing, and I'm sure you're nearly asleep, but this is just what I found interesting about this, to sort of flesh out my insights on it. I don't think there's a whole lot more I can say. The only curiosity left to show you is the fact that the index pulses, I'll trigger on those again. There we go. And then you can see those. I'm just going to give up on the data here because it doesn't look like anything. If I turn the drive off, you actually get to see the frequency change because it keeps reading and transmitting the data off the disks even though the speed hasn't locked in to regulation yet. So here, I'll turn it off, and you're just going to see it die. I'll let it come to a stop. It does take a little while. There's big, heavy, wide platters in there. Still going. Man, that takes a long time. Still going. And stopped. All right. Start it up. And there you go. You can see the thing come up to speed. Then it'll stabilize right there. And it's on. You heard the head go weep weep. It does a sweep. For those who are curious, this is Seagate ST-238R. It's one of their RLL drives in the mid-80s, I think. Mid or late 80s. I forget when it's from. I don't even remember the capacity. I think these are 40 megabytes or 44 megabytes or something, depending how you format them. I've got a few around that I use. This one still works. That's about it. I'm going to stop. We're into this 40 minutes and 40 something seconds. Cheers.